Hi, I'm Michael Coviello, and my dissertation explores the procedural generation of alien planets. So what is procedural generation? Well, it's the concept of generating content using algorithms instead of making it all by hand. These algorithms can generate the content from scratch or pick from a selection of handmade assets and programmatically place them in space. This can be used for terrain, character names, art, and much, much more. It's not just for generating worlds. For example, a planet's ground might be completely procedurally generated, but there are some hand-designed structures procedurally placed on it. It's also very useful for generating fauna, as it's much faster than hand-designing, say, every leaf in a forest or every blade of grass in a field. Games like No Man's Sky, Terraria, Minecraft, Spore, Crypt of the Necrodancer, and many, many more have used this to generate the terrain that makes up their worlds, with No Man's Sky using procedural generation for almost every element of the game. The reason that it's so commonly used is because you can represent huge expanses of terrain or amounts of data without using massive amounts of storage, like No Man's Sky's 18 quintillion worlds in just a 10 gigabyte game. So what are my project aims? Well, for my project, I first want to research the ways that current games implement procedural generation of terrain, be that the ways that planets are generated in No Man's Sky, or different biomes are generated in Minecraft, and analyze these to find efficient ways to procedurally generate terrain. I want to generate my terrain using a chunk-based system, and I want to make sure that this is efficient and not taking up absurd amounts of memory to run. I will also be comparing different techniques for generating different types of terrain. This involves experimenting with combinations of octaves of noise and mathematical functions applied to it to get different effects, and I'll talk about this later. I also want to procedurally generate textures for the planet that are dynamic and dependent on the terrain. For example, the peaks of mountains are white while the bases are brown. In terms of technologies I'll be using, I plan on using Unity 3D for my prototype. It's a powerful game engine that's been used to create AAA games and is well suited for the procedural generation of terrain due to the ease of generating mesh in real time. While many other popular game engines can also do this, I found that Unity makes it the most straightforward, and I've had some experience using it for personal projects and university work in the past. Inside of Unity, I'll be writing the code for the procedural generation in C# using Visual Studio. This is one of the 3 scripting languages that Unity supports, alongside UnityScript and Boo, and it is the most common of the languages for Unity programming, as well as one of the most common languages for general games programming. I haven't had experience writing code in C# before, so I've dedicated some time alongside my prototyping for learning all of the main features of it. I will do this both by following online tutorials, independent learning, and the Code Academy C# course. I have had experience writing in C++ and Java before, and concepts from both of these are carried over to C#. For any hand-modeled 3D assets, such as rocks, structures, or any other assets that aren't going to be procedurally generated, I plan on using Blender 3D. Blender is a powerful, open-source 3D modeling and animation application, which I've had a few years of experience using when I was younger and should be more than capable of any modeling I'd need to do for this project. I've chosen to use Blender over other modeling applications such as Maya and 3ds Max due to my experience with the program, and that for simple modeling tasks like these, they are all more than capable and have no particular benefits over each other. I plan on following the Agile software methodology while writing my code, and I've chosen Agile due to its flexibility when compared to traditional software development methodologies such as Waterfall. In order to make sure that I stick to this, I'm going to be using Team Gantt and Trello for my project organization. Team Gantt is an online Gantt chart application that's allowed me to plan my project out ahead of time, defining the deadlines and dependencies for different parts of my project. It makes it easy to visualize how much changing a deadline will affect tasks further down the line, which is helpful in case some tasks take longer than anticipated. I'm also planning on using Trello to manage my sprint backlog, noting down the different things I need to implement in the prototype, their deadlines, and all of the tasks required to complete them to allow for an organized implementation of each task. Here is my Gantt chart and the tasks that I have planned out over the next semester. As I mentioned previously, I plan on continuing to learn C# and performing my background reading while working on the prototype. There are various dependencies on the Gantt chart that specify what tasks I need to complete before I can move on to another task, indicated by the connecting lines. In my prototype section, I have a lot of subtasks in a checklist that I can tick off as I go that specify what steps I need to take next, and these steps are all planned out on my Trello board as well. One of the largest risks in my project is the many dependencies in my Gantt chart. If I fall behind on a task, it could potentially set back my whole project. If this happens, my plan is to focus on the more important tasks, while tasks that take less time, such as placing hand-modeled objects, can be implemented at a later point. Team Gantt is especially useful for this because it allows you to visualize how delaying one task's deadline will affect the others, so this should also help with this. I've planned out all of the tasks required on my Gantt chart and Trello board, and the subtasks required to complete these, which should also help to avoid unforeseen difficulties. Also, it's possible that I will run into more difficulty than expected learning C#, but I've started this early, and I'm taking the Codecademy C# course alongside what I'm learning independently to ensure I understand the basics of the language before moving on. This should help reduce the risks of getting stuck. This is what my current prototype looks like. As you can see, the chunks being loaded on screen are hidden and shown to follow the camera's position. Here's another angle that helps to visualize this. These chunks are procedurally generated using the coordinates of the chunk as a seed for the noise, which helps eliminate any seams between them, and means that if I hide a chunk and then show it again, it will always be the same chunk being shown. As you can see here, I keep a history of chunks that have been recently shown, and these are stored even after they are hidden for a little while, until a history dictionary becomes full and they are overridden. This was done to avoid re-rendering frequently rendered chunks. As you can see, this is random 2D noise, which isn't ideal for generating terrain because of how blocky it is. To make this more suitable for terrain, we can take octaves of this noise, scaled in or out by 2 times, and overlay them on top of each other, using half the opacity for 2 times the noise. This results in Perlin noise, which is much more suitable for terrain generation because it's a lot less blocky and has more detail. The combinations of octaves and their opacities are what I plan to explore next in my project. Finally, here are my image references, and here are my background reading sources. Thank you for listening.